Okay, welcome back, and we are going to take a look here at what I've gotten done on the code here for this Ultima tile-based paint high speed, hopefully, paint, I call it paint, but draw routine. So I already kind of showed some of this in the introductory video and went over a little bit of it, so I won't go too much into this, except for the parts we haven't really talked about yet. So what we've got here is we have basically, we're going to construct eventually this kind of main loop here will control, I've got it set up now so when you hit the Q key, it exits. Eventually we'll expand this to have movement keys. So we're going to get in a little more of the code breakdown here. When we exit, we basically restore the text screen because we are calling from basic at this point. Basically just do a main loop here, and we do our animations for the tiles. Now the water tiles are animated with just, fairly hard-coded. We are doing a loop, and we're using the branch plus method, which is where we start at a value. We count down to 0. When it trips past 0 to FF, that falls through. Otherwise it branches as long as it's not. The negative flag isn't set. And then at that point we basically preserve the bottom 2 bytes because we're moving the water down in memory. Well, really up in memory, but the tiles are moving down visually. So the last 2 tiles are getting moved to the top, and everything else is being moved down from what you visually see. So we do that here, and then we restore those 2 tiles at the top. We do the same thing for each of the tiles in their memory spaces. They are 32 bytes apart, since they are the first 3 tiles. There is no, in these Ultima tile sets, surprisingly, I was surprised, there is no tile that is a blank. Now, Ultima 4 did not have the blanking routine. Oh, yeah, I guess actually it did. Ultima 4 did. So they must have did it programmatically. I personally would just use the 0 method, the method, I mean, where tile 0 is blank. And you just put a 0 in then, because 0 is easy to remember as either, blank, background, nothing, Anyway, and then what you do is, as you calculate your, this is the map buffer, for instance. So this is the 11 by 11 grid of what you see on screen. So then as you figure out what gets blanked out, you just put zeros in those spaces, and then call the draw routine to do that. Anyway, so that's one thing. So we do we animate the water. And get to the thing here, and then we just basically paint the screen. We actually do this in this case. We do the animations after we've painted the screen, just so they're ready to go on the next loop. It probably doesn't matter which way you do it, really, but I just ended up doing it that way. But I do want to have, there is going to be a check in here at some point. Right now, it just forcibly okay. So right now, just so you get enough context for what's happening here. Right now, this is important for what we're going to eventually do later with the optimizations. Right now, this paint, I call it paint, but the thing that puts the tiles on the screen does all of the tiles, and it has no logic to say this is not an animated tile or this is a tile that was previously shown or something. So it does not differentiate. Every time you see these animations happen, I'm going to show you in a minute, the entire 121 tile set, the entire 11 by 11 screen is being repainted each time in full. And the tiles are being animated in full, which, I mean, I guess if you have the animated tiles, you would do that each frame. But so each frame you see, every time you see that water move, the water's being animated and the entire screen is being redrawn. That's important to realize what's happening with that for the performance aspect to what you see. All right, so let's go ahead and take a look at that. Now, this is set up once again. We're running at stock speed, 1.0, and we are. This will run. It won't do anything until I hit a key, and then it will start the machine language program. Okay, so again, these tiles are being animated, obviously, and then each time a tile is animated, the entire screen is being redrawn, the whole thing. So you can see this is running very fast. My estimates on this are something like possibly 12 frames a second. It's at least 8 or 10, and I got to do I still haven't done the and I'll do another follow-up video where I record this, and maybe I'll use this recording to see. In fact, I probably should. Well, I'll make another recording for the actual Ultima games to compare them. But you can see from my perspective, this is very fast to be doing the full screen redraw. This is not even the optimized way to do it. Eventually, like I said, you'll only redraw the tiles that are animated, and if you move around the world, you'll only update the tiles on screen that need to be changed. So movement should be pretty quick, and this is very fast as it is. Now again, there are certain things that are not happening here. On the other hand, there isn't much to do because you'd be idle at this point. So when you're idle, this is all it should be doing. There really aren't any checks. Unless you're in the game, you're talking about the Moongate phases. Well, even then, it's a turn-based game. It really shouldn't, it might wait to hit the pass button for you if you do that or whatever. But it's a turn-based game, so when you're not moving, this is all that should be happening. So this should be the speed Ultima should be running at when you're just standing there for anything like this. And you would get this speed no matter how many water tiles are on screen, because this is doing a full redraw. So if you had one tile or the entire screen filled, it would move this fast. So I'm very happy with the speed of this. This is very fast compared to, and maybe I will have to do a comparison here for, let me actually pull up, okay, let me go off screen here and pull up the Ultima 4, and we'll do... This is my one of my test discs. Get this re-going here. Sorry for the pause. Okay, so now, as you can see, this is rather slow. At this point, it is animating this, but that is not much. That's literally one character that it has to update, which is a lot less than this. And it's maybe doing the wind stuff, but again, the calculations for that can't be that much, and the moon phases... Actually, I don't even know if it's doing that until you... Yeah, I guess it is doing the moon phases. Okay, so it may be checking a few things, but there can't be a whole lot going on since, no monster is going to come in and be generated and attack you until you pass. You can see that the little flag here, you see how that's semi-random. That's easy enough to do. Like I said, we'll do that. So this, to me, is 4 or 5 frames a second. It's not very fast. And I always wondered about that, thinking that could be a lot smoother. And that's hence why I did when I'm working on what I'm working on. The movement, when you move, and if we have the blanking thing, yeah, see how the corner up there is blanked out? Oh, that one didn't. Okay, so like these two spots are blanked out. So it's doing a line draw kind of a thing. That would take time to do to figure out what stuff gets blanked out. But that's between movement. So in terms of animations, it won't matter, and because the animations will be done in between the frames anyway. And then it'll affect movement speed, which you'll have to come up with a fast routine for that. I would like to implement that, so I may try to come up with that. I'd come up with it on the Atari when I did a thing, when I was working on my game on the Atari. And I ended up using, again, like a table of kind of pre-calculated lines, so that it would just be able to just whip through the lines and check to see if it's a blankable tile. And I also have my tiles set up. Again, if you were to make a game, if you were to truly make a game like this, just design considerations, one thing you want to do is you want to group your tiles together. They did them this way for whatever reason. But what you really need to do is for checking things, speed, you need to group things together by, as much as possible, by things that can't, that blank out, right? That have a blanking thing. So they're all in one chunk. They're all in one sequence, one group, or together. And all the stuff you can't walk past, like water. Because you want to be able to check, so this is 0, tile 1, tile 2, for instance. So you can't walk past these, right? So when you're doing your checks of movement, if you were, let me go here, and you see blocked, you want to be able to check below 0 or 0, or 0. Well, let's just say this was not 0. Let's say this was 5, 6, 7. You want to be able to check this first range and say, okay, all of my block tiles are 5, 6, and 7. So is this tile that I'm trying to move on below 5? If it is, allow movement. Is it above 7? It is, allow movement. And if it's not, then you can't move. And that gives you a very fast check instead of checking individual tiles all the way down the line. Same thing with the blanking thing and some other things too. Animations, well, not animations. Well, maybe animations. The animations may be handled differently depending what you got, you know, because the tiles would be different that way. But anyway, let's get this attack over. Well, so let me go back to our main thing here. Anyway, those are just an example of some design considerations that will affect and can affect how the performance of this is. If they didn't arrange their tile sets that way, they could be leaving an awful lot of, you know, doing a lot of checks every frame, because you have to check every single frame of animation. Or no, I'm sorry, for movement. Well, for movement, but for animation, you know, and things like that. So it depends on how you set things up. But with the movement in particular, the blocking and the blanking, with the stuff you can't see, there's better ways to arrange those so that you can do your checks much quicker. Anyway, that's just a overall kind of thing. We'll implement some of that. What we're really interested in implementing is, and kind of going over, hello. Okay. So what we're really interested in looking at here, because again, we're looking at this from a performance standpoint more than from a game design standpoint. I'll mention some stuff about game design because I've already done some of this on the Atari and figured out what works best and all that stuff. But for certain things, but I don't want to get into that just yet. I might do that as a separate video someday of, you know, here's how you design a game like this in terms of your tile sets and stuff like that. For instance, you have 256 tiles you could use because each one of these is 1 byte. So you really have 256 tiles that you could possibly represent on the screen at any given time, any one of. But you want to have animations. Now, the Ultima 4 characters tile set is 256 tiles. They just did 1 set. But for Ultima 5, they did 512 tiles. 16K of memory. So that second 8K bank is mostly animation frames for the various characters and such. So that's where you would kind of say, oh, put your animations into a separate area and only pull the ones you need into your main character set and update within the character set for display when you need them, as opposed to, and preferably sticking those animations under the ROM. But you don't want to take up space within your first 256 characters for animation stuff, even though in Ultima 4 they do, because all of the tiles are represented within the tile set. So even though when you have like an animated character, there's 2 or 3 or whatever it is for each character in the main set. Again, there's little better ways to do that by separating out the animation frames from the main set and only having, you have your main character in the set, but then if there's any animation frames, you put them somewhere else in memory and bring them in when you need them. You would get more unique tiles you could use in the game. So that's a huge, if you're ever doing one of these games, that's a huge thing you want to be doing. You want to be thinking in terms like that. Is how many unique tiles can I make, and any animations go outside of that set and just bring them in. You just copy them in, because that's how it does animations. It'll take this character, and in the tile set, the next character over is the other frame of animation, and it will swap them, or it'll cycle them. In the case of Ultima 5, there's 4 frames of animation. So there's 1, 2, 3, 4, and it will just take the next frame and copy it into the main set and then redraw the screen or redraw your character, and that will animate him. Anyway, those are, again, some other design considerations. Some of that I will implement, I think, here, because I'd like to have that idea. But for the most part, we're really concerned about how to redraw the screen and how to do basic animations. Water is probably the most common one in the Ultima games of animated stuff, because you run into it so much. Characters are also the biggest thing when they're on the screen. Any characters animating. These little flags are good, but you only run to cities every once in a while. And when you're in a city, there's fountains and there's things like torches or fire that get animated in various ways. Some of them are random. Fire, like if it's inside of a square, like a stove in Ultima 5 has a little square, and there's red pixels in there. They're just basically randomly generated. So you can cheat some of the animations really easy and get them really efficient that way. Like I said, for these flags here, you only have to swap these 2 bytes. So it'd be, trivial to do, and you just really have to manage not doing it every single frame, or they'll be flipping like a, it'll be really, really fast. So anyway, so in the code, as I had mentioned before, so what we're doing here is we're looking at the screen, and this is a little bit of a deep dive, so if you don't want to have too much information here, this is going to take a minute. So we're drawing every tile sequentially across the row and then down, and the rows going down. So this one, this one, this one, this one, all the way across, reset, go across, reset, go across. So to do that, we track which row we're on, which graphic row we're drawing, and we also have another variable for which tile across that row we are drawing. And that's a standard, fairly standard X by Y. Except we're not doing it where we just say the row is 2 and multiply to calculate the row. Because the row is not a multiple of 2. So, okay, so when you're doing math in machine language, as you know probably, when you start dealing with odd numbers like 9 and try to multiply it times 2 or whatever, it doesn't lend its, well, you can do 2, but if you're trying to multiply 3 by 11, it gets messy. So the easier way to do that, without incurring that, because you still have to check when you've hit the end of the row anyway, and you got to reset stuff anyway. So we do one check here. We set the map position index. This is our position within the map buffer. So that's our tile that we're going to grab. And then screen tile X is our position across the row. Both start at 0, or start at FF. We start these at FF because we're going to increment them at the top of the loop. The reason we do that is because we want to be able to catch the last byte that we process, which is, we really process 120. Remember, there's 0 based. So 0 to 120 is our map. 121 represents we've done the map. So I didn't want to put this at the end because I don't want it processing 121. I want to stop once we've reached 121. So the quicker way to do that was to start the indexes at FF, and then at the top of the main loop for the tile, increment them. That way we get to 2121. As soon as we hit 121, we leave. All right, so then we get our, and oh yeah, and then the screen position, again, same way. We start FF, we increment that screen position. That brings us to 0 for the first time through the loop. It starts at 0. We compare with 11, and again, we want to draw tile 10. So we got to increment until we hit 11. Now tile 11 does need to be drawn. It just doesn't need to be drawn on that row. It needs to go down because, again, 0 through 10. This is tile 11 within the map buffer. So once we hit that, we jump around it if it's not. Whenever it hits 11, now we can reset to proper 0 because we are about to draw the tile. So in this case, okay, never mind, skip that. So we reset because we're basically doing this comparison before we draw the tile and resetting things within that context to reset to the beginning of the row before we invoke the tile draw. Okay, so we do that. We set our 0. We set our X to 0. That resets the from here to here, beginning of the row, and then we increment the row number, which is what's used to determine which routine we use to draw the row, to draw the tiles that are on that row. And then we set up the jump address. There's a jump address. We'll get into this in a minute. This is tricky self-modifying code type stuff. So we do this to set up which routine we use to draw that row. Again, this could be done a little bit differently, but probably not as fast. So we'll see, probably more memory efficient, but not as fast. Then we go ahead and we get our tile from the map. So now we've figured out where the tile is going to be drawn. Now we get the tile itself. We load A with the absolute X because we know where our map... Remember, this is another trick. There's a lot of indirect usage in this and this type of program. And I'm not an expert in this by any stretch, or any of this, really. I just know how to hack stuff together. So I'm not an expert programmer or any... Like I said, you guys are probably looking at this and going, oh, there's so many better ways you could do that. And if so, go ahead and leave it in the comments. I'll definitely take any advice I can get. But remember, the goal here is speed, not just memory efficiency or the coolest code you can make. Or speed above all else. Anyway, so in looking at the various things about how addressing modes work, we talked in an earlier video a little bit about how this, not that method, the method for getting indirect comma y from 0 page, you have a 0 page address, you get that, you index into that address, it creates an address in 0 page, you then use comma y method to use that 0 page reference as an address, so it takes that, says this is an address, and then it says comma y indexed from that starting point of that address. There's also an absolute method, which you can do with X and Y, by the way, but I wanted to keep Y free. I usually use X because it's the more common one to think about, but you can use Y this way as well. It's called the absolute method, where you take a fixed memory location, or a memory location, not indirectly, you just directly address it, but comma X. It is indirect, but it's not, you're not going there and saying this is an address and then going to that address. This is the actual reference itself. This is the actual specific memory location. And then we get, again, map position. That should be fairly obvious. You're getting the next map position in that buffer, in the map buffer. And then we store that tile in tile index. Eventually, this is what we'll use to compare all the comparisons to say, is it an animated tile? Is it the same as the previous thing in the map buffer and all that stuff? For now, it's just going to give us where we can get our tile. Now, you could, and I did this, to get the actual address of that tile. Again, tile could be 3. 3 times 32 is whatever, and then 96. So you could multiply it. I already tried this, though, or looked at it, and I ended up getting 27 cycles per tile. Now, that's not bad, but it does solve a problem of memory space. But I didn't want to have, let's see, how can I say this? I wanted to make each routine as fast as possible. And then we can see about using a more memory efficient method once I've got a baseline for performance. So all of this right now, and what you see in the this is my baseline. Whatever this ends up being, I'm going to pull this into a video editor and I'm going to break it down into a 1 second chunk and count how many times this updates and get an idea of my frame rate. This is my baseline because it's not the fastest, but it's the baseline for the most straightforward way of doing it. Redraw the entire screen, animate the tiles, and all that stuff, right? And these other methods I'm using. Then we could start seeing about saying, well, what if we change this routine, or that routine? This routine could be made, because even though it's longer in terms of cycles, 10 extra cycles per tile is not really a big deal. But in this case, that's still a couple thousand cycles, 1,200 cycles. Probably won't make a difference, but there are other places that 1,200 cycles would be more useful to be able to, save. And I don't want, once you start saying, change this to make it more memory efficient, change that to make it memory efficient, you start adding cycles, and then it slows down. And you want to see where your slowdowns are. So we're going to have to do these one at a time eventually. But anyway, to check performance. So it's not a lot, but I was going for maximum performance. The faster method is to create a table of address indexes. So it's 32 bytes per tile. So this table just has every 32 bytes, through it. So you just take the index of the tile, you get the low and high address, and you stick that into this is the 0 page. For the tiles, we are doing the 0 page comma y indirect method for getting the tiles. So we stash that address. So that's 17 cycles roughly instead of 27 to calculate it. I'm not even sure this is right. I got to check that and see. I just ran it out and it looked right. It looked about right to me. I didn't really test it. So there may be a faster way of doing this as well. If there's a little bit faster method of basically multiplying times 32, cool. I'll try to look that up. I didn't do any research to see if maybe there's just a simple way of doing that. Okay, and then once that's done, this is the jump table. Actually, the draw tile here. Let's see where we're at here. Okay. Anyway, this, oh yeah, I scrolled down too far. So we derive our address, and then we jump to the correct row routine, and it returns. So this is a tricky way of using. There is no such thing as a jump to subroutine indirect, or with a table. So you can't say, here's index 5, go to this table and jump to the subroutine of that location. So a trick method of doing that is to create a jump table, and we JSR to here, and then we do the jump from here. And then I have RTSs. These are actually just dummies. At one point, I was having problems with when I brought this file into the emulator. It was cutting off the file, and I wasn't sure why. So I had to put in some stuff that I could find easily in the memory. Anyway, this is just testing. So basically, we JSR down to here. So now we've created on the stack a reference point for a subroutine. We said jump to this subroutine. This subroutine, there's an RTS here, but it'll never get here because we jump to whichever this address is. Now, here's the tricky bit. This address is the reference here. Here. We put an iJump, and there's 3 bytes. Jump, and 2 bytes for the address. So we do a +1, +2, and we change this address. Right now, we just use this label so there would be 2 bytes there. You know, I could have used just 0000. But for testing initially, this is the only thing I had. I had the first row, so it was easy just to leave it. So we get from the table, we get our references. This is a way in this MADS assembler to create an address based on a label. So we've got all our row routines, we'll get that in a second, that draw each row of the screen. So each one of these rows is a separate routine, hard-coded. You'll see in a second. We jump here, or we get, I should say, from this reference, from the table here, whichever. Come back over here. Come down here. It's a bit of code to scroll through, so bear with me. Here we go. And we use X. We basically take our X. We load. Okay, we load A with the row number. So let's say the row is 2. We ASL that to multiply it. That's 4. We transfer it to X, and that lets us jump because every address is 2 bytes. So we've got to do multiples of 2. And then we get from the jump table the whatever row address reference there is, and we store it. That gets stored into this jump here. So this is dynamically changing code in this instance. So so when that jump happens, it goes to whichever routine is. Now remember, we have done a JSR to here, JSR to here to process tile. So on the stack, our reference is here, or well, not our reference is here. Our return reference is up here, because we've done a JSR to here. Then we jump from there to whichever row routine draws that row, and it processes that tile. And then, when this routine ends, it RTSs back to where the original JSR went to the jump table, which I can't find now. Here we go, the JSR iJump. So it comes back to here, and then we go back to the tile loop main to loop our tile draw. This is our tile draw. And as the other code you saw, it processes and figures it out. Now, the extravagant part, the insane part of this routine, of these routines, in order to get that kind of performance is, and I've already kind of covered this a little bit in the first video, just to kind of get an example of how expensive this is in terms of memory. Each row has its own routine, and each routine has hard-coded addresses for all of the rows in sequence. So this is line 8, because again we are doing there are 8 rows that are the border. So we start at 0 through 7. So we start at line, if you will. I call it row, but Really, row in this case should refer to the tiles, but anyway, line 8 on the screen. The actual, this first line here is line 8 of the graphic screen, and 9 and 10 and all the way down in sequence. So we run that out in sequence. We use the X method here because this, we get the tile, let's back up a step. We do get the tile using the indirect Y from 0 page. That should never incur the boundary crossing penalty. So it should be 5 cycles instead of 6, I believe it is, because it's a multiple of 32. So it always ends on a page boundary. Any given tile that would be at a page boundary is on the page boundary. So we should never be crossing the page boundary with this. Or if I did this wrong in terms of, well, no, I think that's right. Yeah, because we're not doing a loop. If you're doing a loop, you might run off the end. You might run 1 byte, 1 extra, or something. Anyway, we're not running loops, though. We're running essentially what amounts to unrolled loops here. And that's because if we did that, if we did a loop, which is more efficient memory-wise, all of these memory locations, 2 things. 1, the memory location would have to be gotten from a table. So that's easy enough to do. You can figure that out pretty easily, and I've got a table for that, and that is not so hard to do, but it is a bit more expensive because you have to do an extra get for every row, for every tile. Although I suppose you could possibly, this is what I got to think about in terms of efficiency, there may be a way to, again, maybe we'll do some self-modifying code in here, but either way, you got to get that and you got to stick it in here somewhere, or stick it somewhere you can use it for any given line, right? Because each line is on a different, you can see it's not sequential, so you can't just calculate it. And even then, if you just added 40 bytes, it's still calculating, and there's a lot of cycles taken up with that as well. So by hard coding this stuff, and we do the X method here because, again, it's really the same number of cycles than if you didn't have the X, or less cycles than doing this method if you did a 0-page option. So it's, you know, again, I think we showed in that you basically can save 3,800 cycles by doing it this way as opposed to doing it that way. By having the hard, because you're saving at least 1 cycle per store, per reference to the screen memory. Let alone the actual get that you would have to incur. It really, if you think about it, it'd be tens of thousands, probably 10,000 cycles or more, or something, or several more thousand cycles to get the row first here in some fashion and construct it. But again, we may be able to actually, there may be a way to get the starting address for the tile for the row, and just leaving that until you update the row. That's the next thing I'm going to probably try to work on, is to see if that's possible to say, okay, we got 11 tiles on a row, so the row starting points for all 8 of these is the same, right? It may be worth it to just hard code these in, you know. Well, it's actually, now that I think about that, might not be a bad idea when we change rows, because that would only incur a one-time, you know, penalty of running those bytes out for 11 tiles, which is a little bit more efficient. It's time, but it's not as bad as doing it per tile. Anyway, oh, bumped the mic. Anyway, so again, this was the straightforward method I wanted to do. I want to try it as an unrolled set of, you know, no loops, and see how it performed, you know, and see what it did and how much memory it took. It is extravagant for memory. If you've seen the initial video, you'll give an idea. And we'll cover that in a second. But you can see, performance-wise, it is very fast. Remember, this is full-screen redraw. I have to keep reminding myself, this is not like looking at the game or any other efficient optimizations. This is just straight up animating the tiles, redrawing the entire screen every frame. And that is very fast. I did the Apple II, because of the graphics memory issue and how it's laid out, and because it actually runs at, I think, 0.9 megahertz, so it's a little slower. It's like, I think the 64 runs around that speed too, and some other machines ran more like at 1 megahertz. So it's got a little bit less to work with on that regard, in terms of performance and speed. So having this kind of performance on a full screen redraw, we say full screen, it's not truly the whole screen, but full screen for these purposes would be a game, is really good. And there's ways to optimize that too. We're going to be looking at that down the road. So yeah, so I may see about doing some kind of one routine where I just change these addresses. I could put labels in here. It's not a bad idea. I might try that and see what kind of performance penalty that incurs. Because you would have to, whenever you change the row, but it's only done once per row. So it wouldn't be as bad, but it is a lot of addresses to change because you've got 16 lines. So every tile is 16 lines tall. So you'd have 32 bytes you'd have to change. So I have to do the calculations on, getting from the table and putting it out there. Now, here's the kind of offset to that. Okay, well let's actually just do this first. Then we'll talk about memory issues. So we do this for every row. So each row has its own routine, hard-coded. And as you can see, it's a lot of memory. So we go all the way down. Every row has its own hard-coded situation. They share this. I might be able to make it a little bit more efficient by making this a subroutine. Again, I haven't really optimized this yet to see. So, but this is not that many bytes. It's 1, 2, 3, 4, 5, 6, 7. It's 8 bytes. Even putting this into a subroutine may not really be much of a memory savings. And that's the thing about machine code you got to keep in mind. Sometimes very simple tasks, even though you're replicating the exact same code over and over, it sometimes isn't worth putting it into some kind of subroutine because this is going to be, you save a little bit, but not a lot. Because they're so simple and quick to do. There are a few things in machine language you can just do really simply and easily, way simpler than other stuff. So this is load A, 2 bytes, that's 3 bytes, 4 bytes, 5 bytes, 6 bytes, 7, 8 bytes. So this should be an 8-byte routine. If we were to JSR that and create this into a subroutine, we have to add an RTS, so that's 9 bytes, and then the JSR takes 3 bytes to call it. So yeah, there's some savings, but it's only about, 4 or 5 bytes per routine. So 5 bytes per routine times 11 routines is 55 bytes. It's like, yeah, it saves. It's more elegant and efficient. You do add a little bit of a cycle overhead. But don't forget, this is also, these routines, even though it says row, each one of these routines is drawing one tile. It's not drawing the whole row. This is just doing one tile. It's just invoked multiple times. And I did this way for 2 reasons. Well, one was speed, but also, in the end, I want to have some ability to address an individual tile on screen. That may not be the best way to do it, but I wanted to have things laid out in such a way that I could do that. Although I may change that and just like take one of these routines and change it around to do that. But it's maybe not a thing. But anyway, so again, you have to look at the over-under. You start thinking about these things in terms of, okay, so we put this into a little subroutine, and we save 5 bytes. And probably, well, the cycles don't change because you still have to calculate all this stuff. Each tile has to be calculated. So you save 5 bytes. Yeah, so the memory, if this was saving cycles, and it was 5 or 10 cycles per tile, that might be a little more substantial. But it doesn't really save time because you have to run this calculation for every single tile regardless. Because the tiles are, any given tile could be any given tile. You have to get its address, or actually I should say you have to get where it goes on screen in this case. So there are certain things you can't with this type of game you can't avoid. You can't avoid creating the tile address for the tile because you have to know you have to get the data for the tile, and that's variable. That's why I did the comma y method. And construct the address. I construct the address from a table for speed, and I use the Y method because, well, it's just the easiest way to do it. Because I don't know if I can do this method with a variable amount of information because this is not a fixed address. You can get away with this because it's a fixed address. Or you have to create this address, but then you're adding overhead for doing that. So you just go round and round in a cycle sometimes of like, yeah, you can do that, but then is it really faster? Is it really better? Anyway, so we do all of these processes through the various functions, the tile draw here. And then, okay. And that's basically it. It's just the memory. Okay, so the memory of this stuff. Okay, so the memory. So now, as we talked a little bit about how you might save on that one routine, doing it this way, this entire program, as it sits so far, is about 4 kilobytes. And again, that is an extravagant amount of memory for this. This should probably be about 1K, give or take. And part of the reasons for that is, again, we're going for maximum speed here. So if memory-wise, yeah, you could take, you got to have the map, you got to have a map buffer. You got to have that. Well, that's a buffer anyway. But you got to have a map buffer. This does include map buffers, by the way. It includes these 2 map buffers, which eventually will be used for movement. And it does include a little bit, which I haven't finished constructing, of what this will be eventually a portion of the map simulating the 1 kilobyte amount of data that is held in memory when you load portions of the map from the disk. This is going to, for testing this, for when we test movement and animations, this is going to be the map area right around Lord British's castle on Ultima 4. It is 1 kilobyte. So right now this is 256 bytes. So we got a little bit overhead here. This will eventually be 1K. So think in terms of this routine as it sits. Once I get the actual map put in, it'll be 5K. But it does include a 1K buffer for the map. It includes 256 bytes for the 2 maps. This is basically map 1 is we draw the map from here. When you move, map 1 gets copied to map 2. Map 1 gets constructed from the 1K map data at the bottom, and then we use these 2 maps to compare eventually for where we say, oh, we've moved left. Is this byte, like this one will then go here, or actually move right, I should say. So let's say we move right, all of these will go here, but these won't change. So we'll use that to compare between the buffers so we don't have to redraw tiles, and that will improve performance. And that's a sense that's going to be done either way, because you just have to do that because it's the best way to do things. What isn't efficient memory-wise is this, but it is faster, and this is the address for the tiles. Addresses. The way to do these most efficiently is, instead of taking a 16-bit address total and then copying it in some way, because you still have to index into this table, there's a little trick I learned when I was looking at this stuff, and this graphics row table, which I'm not using because I have everything directly hard-coded. This is, if you would do it the other way, you'd have this table. They split the table into low bytes and high bytes, because that creates a table that, because there's only 192 lines, and in the case of our tiles, there's only 256 tiles, it makes everything addressable, each low and high byte addressable with 1 byte indexing. So if you want row 5, you just set your index to 0, 1, 2, 3, 4, 5, and you get the low byte and you get the high byte, whatever it is, and then you construct your address from that. Same thing here. We got a high and a low, so we use that. Use that to construct our. I'm trying to make this clear, but it's very complicated. It's not really that complicated, but if you've never done this before, it's a little confusing. To get here. So we get our index, tile number 5, for instance, and we index into the tile address table at position 5. Because it is a fixed point in memory, and it is on a page boundary. Very important these tables be on page boundaries, by the way, because otherwise it won't work. You got to have your tables. Any tables like this have to start at 0 on the page. Anyway, so we can use the X method, which is a little more efficient. Again, you only use 4 cycles to grab this. We stick that in our tile address. This is a 0-page address, which will use the Y indexing. And we construct the address for where the tile data resides. And you can see 17 cycles per tile, not so bad. And about as efficient as you can really do that, I think. So we've got this put in. You could calculate this, but it would be probably slower because you'd have to multiply. And again, we'll probably be back to the idea. In fact, I think I already did that. Yeah, that's this method. That's this method, which is you won't need the table, but it is more cycles. And I will be testing this. I will be running this to see if it adds significant enough to be seen in terms of animation speed and everything. My thinking is you ultimately could do it this way because, except on a full screen redraw, the only time you're really incurring the maximum speed penalty is a full screen redraw, because you're forcing it to redraw all the tiles regardless. But anything else, you're going to gain efficiencies. Anything else, you're going to gain, oh, we're only redrawing the animated tiles, or oh, we're only redrawing the differences when you move. So in a full screen redraw, in most cases is not going to be necessary when you enter a town, but there's already a delay entering the town anyway, so it doesn't matter if it takes a few extra milliseconds. And things like that, where you can say, oh, that's already buried in the processing of everything else, you know. You don't notice it. We're trying to focus on the performance benefits and aspects of high-speed animation. How fast can we redraw or draw or get these animations going and redraw the screen? Movement incurs a whole bunch of stuff, because if you're moving and you cross a boundary, it has to pull from disk anyway, and then right there you've already blown any kind of performance that matters. So those sorts of things don't matter. Movement from just one frame to the next, when you're moving, again, you expect that it's not going to be, you know, like you move, just zip across the screen. You expect there to be a little bit of time factor in movement, so your brain is already, you know, not looking to see maximum frame rates out of that. So you can have certain things like that. So this is probably, but this, you know, does incur per tile as you're drawing the screen. So we gotta see what that'll do. Anyway, these are some of the design considerations you think about, and some of the optimization considerations we'll be looking at. So that's, I think that's probably about it. It's probably long enough as it is. But that gives you some kind of an overview of the program and what it's doing and how it's doing some of this stuff. And you can probably, if you're familiar with how to do some of this stuff, you can probably see where some of the optimizations can be done and what we'll be looking at. I already outlined some of the stuff with how the screen redraws we're going to mess with next. But we do have a bunch of buffers in here. Like I said, you could save memory here by doing the calculation method, and I probably will do that. But the reason I did it this way is I wanted maximum speed in all places first, and then we'll start adding or optimizing and stuff. But if we do this method, we don't need the table, which saves memory, and that's cool. So that's fine. We'll see about anything like this. This is going to take a lot of figuring for calculations to see if my ideal would be to get this down to, you know, one routine, still unrolled. I don't think I want to run a loop, because as you draw every tile, if you do a loop, here's the advantage of this. So we do a increment X, and then we do a decrement X. I didn't really explain these. So we get the tile data, and we store it at this X position for whatever position on screen it is. Then we increment to the next byte we need to get, and we increment to the second screen position. This does them in pairs. So that's the first byte of the pair, because each one of these is 2 bytes wide. So 1 byte, 2 bytes. You know, 1 byte, 2 bytes. So we do the first byte, and we increment to the next position and the next position for the byte to get from the tile. We load that. We store that at X position because we've incremented both of them. But now we increment Y for the tile data, and we decrement X to put us back to, essentially, you got to think of it as, give me 1 second here. Let me see if I can find. That's not it. Hang on 1 second. I have if I can find it. No, wait, yeah, no. My apologies. There was one thing I wanted that I did not have set up on here, and I need to find. Okay, here we go. So I showed this in the other program, the other one where that kind of broke down, the previous video that broke down how I made the tiles. So each tile can be considered to be a 0 position and a 1 position on any given row, at least as far as the way we're indexing this stuff goes. So we start at 0, we increment to 1, and then as we go, when we set up for the next row, we decrement back to 0. This is the X position, the X value, to put it back to byte 0, you know, the left byte, if you will. Left and right bytes maybe is a good way to look at it. So we repeat that process all the way down. Again, there's a lot of repetition here, which theoretically could be reduced in code, except for this. Everything about the performance of this, for the most part, relies on this. These store operations and the place that they go on screen, getting this row, line, if you will, on screen of that position to be here and to then put the byte there, that's everything here as far as performance goes. You do this the other way, the other methods, it's half speed. It's going to be twice as slow, or half as fast, if you will, because of the overhead in deriving and getting this address here, or getting an address you can store it to. Maybe there's a way I could make a... I suppose you possibly... Maybe I just thought of it. Maybe you could, if you really want to get complicated, you make a jump table that does this store, you know? And then you create an index, so whatever line, your line 10, you jump to that jump table. I might try that. I'll have to think if that would work. Because this is the same code. It's just X has changed. So really all you need is the store and a return. It adds a little bit of overhead, but probably not as much as... Well, we'll see. Getting to that is the trick. It might work. Something like that might work. It might be a little bit of overhead, but enough to be justified, you know? But it would reduce the code a lot, because then you'd still have most of this, but you could do this in a loop then. But even then, doing a loop, here's the other trick to that. Doing all of this in a loop, remember, when you do a loop, you generally have... You could do the countdown thing, but every single byte in that loop is some kind of comparison. So, at a minimum, you have a BP... what's my one up here? Hang on a second. The B... Alright, oh no, let's take it back. It's here. I do that with the animation tiles, because you're not animating that many tiles in between the frames. So the amount of... And it's only 32 bytes. You're not painting 121 tiles to screen, you're only animating 3 tiles. So it's a little bit different that way. What we're looking at here is, give me 1 second to look something up. Look up the, so the branch plus, so this is 2 cycles to check, and an extra cycle if the branch succeeds, which means we are getting 3 cycles because we are branching, because you have to branch, we have to loop. So this is 3 cycles per byte, times 32, for any of these tiles, to paint them to the screen, animate them, whatever it is. Well, in this case, it's 30, but, you know, that's the thing. But anytime you're painting, if you're doing paint screen. So let's take a look at that. So that's 3 extra cycles to do a loop. So yes, you save memory, but 3 extra cycles times 32 times 121 tiles. And let me just make sure I did that right. 3 extra cycles to do a loop. Okay? That's per byte. Maybe, let's say half of that if you could somehow efficiently do the petabytes, you know, because again, you can pair them up. It's probably more efficient to do that. So let's say half of that much. So 3 cycles, times 16 bytes, half the tile, because you can do them in pairs without having to do the check. And then 121 tiles to paint to the screen. So you're at an extra 6,000 cycles to do that. Plus whatever overhead there is in getting this address to be where it needs to be in that loop for that row, for that thing. That, again, this is why I did it this way, because when I started doing these types of calculations, I was like, man, there's 5, 10, 20,000 cycles being laid out here that are going to seriously affect performance. Or at least I wanted to see, again, what my maximum performance would be without any of that, before you try any of that. So I'll look at some of this stuff and see if maybe it might be possible, but this to me is certainly the fastest, it's not the most efficient way, memory-wise. It is the most efficient way, performance-wise. So that's kind of, that's what I'm looking at. Next, so the next steps here, real quick, and then we'll wrap up, are going to be implementing the map. I want to have a real map. This is just a dummy map I made up that only fits within the buffer, just so I had some animated tiles and some other stuff to show, and we could see how fast it draws. So the first thing to do is I'm going to get the map from Lord British's Castle from the disk on here, so that we can actually write a routine to do simple movement within that buffer and construct this map to display as you move around. Obviously, there won't be any reads from disk, so it'll only go to a certain point in any given direction. It'll just stop. You won't be able to go past that point for movement. But I think I'm also going to put a routine in to hit a key to teleport you like back to the top left corner of the map, just to see, so we can implement the full redraw on movement, which shouldn't really look like anything. It should be fine, but I just want to have it just to mess with it, just to see what it looks like. So we got that. So we're going to do that, and then we're going to do, and we're going to implement these other things. Now, the one thing I'm not sure about I'm going to do is animations. The water is an obvious one, probably a couple of others. I'm not trying to create an engine here, so I'm not really trying to make a full-scale animation, you know, all the animated tiles and stuff. There are a few that I want to do. I think water's enough for now, and maybe the town ones, just to proof of concept the idea of flipping those 2 bytes, because really you're just randomly, periodically, because if this is running at 10 or 12 frames a second, you don't want that flipping 10 or 12 times a second. It'd be way too comedic and ridiculous. So we might put something in logic-wise to check that, or to skip that every 5 or so frames or something like that, and do it semi-randomly. Because in the game it does it semi-randomly until it'll flip, then it'll wait, and then it'll flip, then it'll flip, then it'll flip. So it'll be like a random timing. So I'll figure something out with that, and maybe do these on the towns just because it's kind of a neat little visual. And this town, this is Britain basically, and Lord British Castle is there, so I could, since it's part of the map, I could do that as a way of just having a little more animation thing. And it's a very simple amount of code to do the animation for that. So I may implement that, and then we implement the when you move, the screen comparisons, and doing animations only when you're basically idle, of only updating the screen animations like that. Again, the phases I would do this in is the first way I would do is to do it the quickest, most obvious way, and the simplest way. So the simplest way, just as an example, to do these to track these animations, because as you're coming through the buffer, you say, "Oh, I found water. I need to animate that tile." So you go and animate that tile. But you've animated this tile, and you draw it, and then the next one is the same tile. Well, you got to have some way to know that you already did that animation, because you don't want to animate each tile separately, because then these will all get all out of sync. So you have to have some way to track that. But you don't want to be spending time going through the buffer, or going through whatever buffer you create, scanning and looping and all that stuff, even though it's not very many bytes, or tracking a certain amount of saying, oh, because I could have 3 tiles that animate, I could have 2 tiles that animate, I could have 6 tiles that animate. So the most straightforward way to do it is to create, just like the tile address tables, you create a 256 byte table. That's a flag, and when you hit tile 1, you set that to 1, and then the next time you find tile 1, or anytime you find a tile that's animated, you say, oh, is this an animated tile? Yes. Has it been animated already? Oh, yes, it has. Okay, so just go to the draw routine then. Just skip the animation. That's the most obvious way. I'll probably do that first. Just, again, some of this is about, again, I'm not an ace programmer here. So for me, it's like, I want to do the simplest method. That's the most certain way to work before I try to get fancy with code, and clever. The cleverest thing I did in here, to give you an idea of my level of skill, which is, I'm okay. My cleverest bit was probably to do the jump tables this way, to create the jump table, to create a routine here, JSR to this, construct this, and modify it dynamically, and then return from here up there. That's probably the most clever thing I did in this, really. Everything else, this is just hard-coded, hammered out, straightforward. There's not much, cleverness in any of this stuff. So anyway, so I'm going to try to do things that way and just get things working first, and then we'll see about a more efficient way of doing it. Because don't forget, you do have to check each tile as you go, so you want a fast way to do it. And a fast way to do that is to just grab it, index into a table. Since the table is will be in a fixed location, you can use the comma X method. So you just set X to the tile number, comma X, grab it, grab the byte, and you can do a quick compare, and that's per tile. So remember, as we're doing all this drawing and animating, every time we can do a check per the whole tile and maybe not draw the tile or not have to update the animation, that's a win. That's a performance win. So that's what we want to look at, is say we can spend a little bit of cycles on checking things at the tile level because we only have to do it 121 times. which is not nearly as impactful as 5,000 times or whatever, 3,700 or whatever it is for how many bytes do we have in a? We have 32 bytes times 121 tiles. Yeah, 3,800 bytes. So if you do any of these kind of checks and compares on each byte in each tile on any side of it. So for instance, this 3,800 could represent getting the byte, which we have to do, and it could also represent finding the address for where it goes on the screen, and then for that byte, and then placing the byte. So this starts to add up quick after a while. The more you can save that way, the better. So that's about it for now. And like I said, we're going to work on implementing these other things and revisit later and see what I can actually get put together.